I just said. Oh well. Here we go. So, big ideas, calculus. Average rate of change as change over an interval, or slope of a secant line. How do you find change between 2 points? I'll call them A and B. Talk to me, people. F of B minus F of A over B minus A. So if you were asked what's the average acceleration, then how would you find that? What is average acceleration? It's change in velocity over time. So you do V of A minus V of B over B minus A or whatnot. All right, you with me? Okay. It's often the case that you're given a table and you use change between 2 points to estimate rate of change at some point inside. There's this derivative versus secant line relationship. This can be approximated, used to approximate the derivative at some point C. But it is crucial that you understand it is an approximation, not exact, unless it was a linear function, I suppose. Are you with me? If a curve is concave up, is this, do I have tangent line? It's later, isn't it? Never mind, that's later, sorry, scratch that, okay. The idea of a derivative then is to take the change between these 2 points and get them closer and closer together. How do you get the points closer together? A limit, okay? Now you need to recognize all 3 definitions of the derivative. Notes, I could write them here if you like. If you want to review them, great. But I would definitely say if you see a multiple choice and you see a limit with h in it, with an h in it, they might as well just scream at you, hey, this is a derivative. Okay, but you need to recognize when a problem is a limit problem and when a problem is really a derivative problem. We've probably done something like this over and over again. Actually, let's go as x goes to a of sine of x minus sine of a over x minus a. Now it would be super duper if you saw that and you said, oh, obviously that's the alternate definition of the derivative. This kind of thing. And after you say, hey, that's the definition of the derivative, then you would next say, okay, what is it the derivative of? And it's the derivative of sine. And then it would be super if after saying it's the derivative, then if you actually take the derivative, that would be really great. So what's the derivative of sine? Cosine. So your answer to this is, if it said, what is this limit equal to? It's obviously not a limit problem at all. It's a derivative problem. It's cosine. Okay? That is guaranteed to be on a multiple choice. It's guaranteed to be on final. Guaranteed. It's on every AP test that ever was. At least once. Right? Derivative techniques. You should know lots of derivatives. Let's just make a quick little table here, shall we? You know that the derivative of e is e. So if the function is e, its derivative is e. You know the derivative of log is 1 over x. Let's go with the derivative of sine. Cosine. The derivative of cosine. Negative sine. I ran out of room. You work out how much room you have. The derivative of tangent. Secant squared. The derivative of cotangent. Negative cosecant squared. The derivative of secant. Secant tangent in any order. And the derivative of cosecant. Okay? The derivative of arc tangent. 1 over 1 plus x squared, the derivative of arc sine. Okay. Those are just things you should have at the ready. You follow? Okay. At this point, you should be well beyond making dumb power rule, product rule mistakes. You should know that the derivative of whatever x squared cosine is not 2x negative sine of x. You should know you don't take a derivative on products by just taking the parts. That's garbage. You're way past that. You should never make that mistake. Obviously, on the chain rule, you need to know how to use the chain rule. Don't forget to take the derivative of the inside quotient rule. Do you remember your quotient rule? You put it up. Low D high minus high D low over the square of 1 through. Okay. Implicit derivatives, that's, you guys are actually pretty good with that. Remember, horizontal tangents, if dy dx is 0, vertical tangents if dy dx is undefined or 0 in the denominator, okay? So if I asked you, hey, where's this weird curve that's not a function, undefined or horizontal tangents, you need to know how to do that. Related rates you're actually pretty darn good at. Second, third, etc. derivatives, I guess I'll take this second to write. Be careful of notation. Notation is important. If I, for example, said, hey, f is e to the x squared, and I asked what is the second derivative, then by all means show me what the heck you're doing. What's the first derivative? Times 2x by chain rule, and then what's the second derivative? First stays the same, times 2 plus second stays the same, x squared times a new 2x. But what I'm talking about here is readability. Back to the notation here. I can't tell you, most of you are well beyond this, but some of you are still saying kind of basically stream of consciousness math. Like here's the function, and you're finding the second derivative, and here's the first derivative. I didn't label it, so I hope you can figure out what I'm doing. And here's the second derivative. Again, I didn't label that, so hope you get it. Let me be clear, on the agent test, they will not spend 1 second of their time trying to figure out what you're doing. If you don't label it, you're done, okay? So please label it. This is the derivative, this is the second derivative. Never evaluate until showing the derivative first. For example, if I said f is whatever, x squared, what is f prime of 4? If you just said, oh, well, that's 8, because obviously the derivative is 2x, and 2x times 4 is 8. Well, that's terrible. Okay, you must show the derivative first, then put in 4 in 2 steps. It's the derivative at 4 is 2x. Hey, I'm about to put in 4. There I put in 4. Show it that way. Understood? Okay. Do you know how to use a calculator to evaluate a derivative? Yes. Good. Finding tangent line and a point. Tangent line is obviously point. When you do the slope, show that the slope comes from the derivative. Don't just say, hey, the slope is 2. The slope comes from the derivative, and the derivative is this. Okay, show that. Communicate. Then write point slope. You often are asked to use your tangent line to estimate. Tangent line is often not just the goal here. For example, if I said use a tangent line to estimate f at 2.1, then the idea is, well, At 2, they're right on. Their tangent line is right at the curve. At 2.1, they're doggone close. So I could say, well, the tangent line at 2.1 is this y value, and that's really close to the curve at 2.1, yeah? You still write the tangent line, and then you put 2.1 into the tangent. Make sure you use, this is an approximation, not an equal, it's an approximation. We haven't done this a lot, but tangent lines over or underestimate based on blank. Will the tangent line here over or underestimate the true function value? Underestimate, because the tangent line lies under. Why does the tangent, they won't take because the tangent line lies under. I understand that, it's true, but that's for your understanding. As far as actual calculus to back it up, why does the tangent line lie under? Because the curve is concave up, because f is concave up or down. Okay, so to justify, if they say, is this tangent line estimate an over or underestimate, you have to get into the second derivative. You'd have to say the second derivative is positive on the whole interval, and therefore the tangent line is an underestimate. You follow? Okay. Applications of derivatives, finding relative extrema, justified at the first or second derivative test. The first derivative test, conclusion. There are two, obviously. Let's just do one of them. F has a max. Let's go with a max at, it could be max or min, but let's just do an example of that. At max, a max at x equals c because f prime changes from positive to negative. Okay, now that's the first derivative test. Basically, you're saying, hey, this is what the slope is doing around that point. Second derivative test is different. It's easy to get the two confused. The second derivative test conclusion is not so much about what's happening before and after, but what's happening at C. So what are the two things you have to do to conclude max by second derivative? F has a max at x equals c because I assume you're writing here and not confused. I'll give you a second. F prime is 0 to establish a horizontal tangent, and F double is negative at that point. It's not before and after, it's at that point, this is what's going on. Why aren't you freaking me out, man? I feel like there's some kind of stalker coming in my room every minute. I love it. Constantly in fear. Martin. All right. If you weren't so agreeable, I'd be terrified. Optimization, it's sometimes subtle. You have to read very carefully, be very analytical. There's a problem. I don't know if it's on this review, but it was on a review I was considering. It was just said, find the point nearest to the curve. Now that doesn't slap you in the face obvious optimization, and yet that is an optimization problem. Just ask yourself what you're trying to optimize. Get an equation of two variables if possible, and then do your derivative. Okay, first derivative test. Absolute extreme is a little different animal. You need to read carefully for absolute versus relative. If it says the max, that implies absolute extreme, not relative. The max is the max. Absolute, not everything has, not every situation has an absolute max. If you have continuity on a closed interval, test. And hopefully, as you know, absolute extrema occur at endpoints or critical numbers. The first thing you would do is state that. Then you would say, hey, here's the critical numbers. The critical numbers are where the rate of change, which often equals the derivative, equals 0. Let's just say the derivative equals 0. Then you find the amount at each candidate. Hey, here's f at this endpoint. Here's f at that endpoint. Here's f at the critical number. Based on that, the biggest one is this one. And then you conclude. That's step 4, conclusion. Okay? Behavior of graph, connections between the graph. Let's go here. F and F prime. Where F is increasing, F prime must be positive. Now that's used in lots of levels. It could be used in an equation. It could be used in a graph. It could be used in a table. Remember the rule of 4. This permeates all calculus. You need to be able to understand math in verbal terms. Hey, the function is changing at a rate of 2 meters per second. That's a rate of change. That's a derivative. Analytical, graphical, and numerical, or table. One of the free responses on Planet I'm using is a beautiful blend of all these. It's really a great problem. Okay, F is increasing if F prime is positive. F is decreasing if F prime is negative. F has a max where F prime changes positive to negative. Now I know that appears in the first derivative test, but it also appears in a graph. If I gave you a derivative graph like this, what would be happening on the original function f at 1? There's a min because the derivative goes negative to positive. Okay, so these are big ideas and all. What about a horizontal tangent? F has a horizontal tangent if f prime is 0. Now all those things could also be talked about in terms of f prime and f double prime. All that stuff. F, where f and f double's relationship. Where f is concave up, f double is positive. Where f is concave down, f double is, and where f has an inflection point, f double is 0, changes sign. I have one more thing I just thought of. I don't have any notes to it. I'll come to that in a second. Position, acceleration, and velocity. Using derivatives, talk to me about some relationships between those. Give me 2 relationships there. Velocity is the derivative of position. Position could be called x, it could be called h, it could be called s, is pretty common. But it's usually functions of time. What else? Acceleration is the derivative of velocity. It's the rate of change in velocity. I guess you could give me one more fact. What else? Acceleration is the second derivative of position. Okay? Okay, differentiability. There are 3 reasons derivative doesn't exist. What are they? Sharp turn. What else? Any kind of discontinuity. And so this one, if I have dy dx is 2x over y, I would have a vertical tangent where y is 0. So anywhere there's a vertical tangent, the derivative, I have a derivative there, but it's undefined. I have a tangent slope, it's vertical, but as far as the numerical value, it's undefined. Follow? Okay, That's what I wanted to go through. I think that's not a bad start. Any questions? Anything I missed that you see? All right, cool. 68. Do you have questions on 68, please? Do the last problem set of the night, Dave. Here, baby. Hell of a year. One, did you say? 23. 25. Against the wind.
And then the answers to the replacements.
The answers to the replacements.
Which is 20.
Let me get those pasted in here. Strangers in the night, exchanging glances, wandering in the wind. What were the chances? Alrighty. Okay. One. Number one. Natalie, are you a track star? You good track? Yeah. I saw you on the whatever athletes of the future, whatever that poster is in the gym. You know, fun with everybody.
Oh, yeah.
Like the pictures. My daughter's basic track. That's what it is. It was basic track. Good basic track, man. That's pretty impressive. All right. Do you have a equation for me? Is that what part A was, I assume? Is A the part? Do you have A? Or do we need to talk about A? Talk about A. So the base is square with x by x dimensions, and the height is y. The base is $8 per square meter. The sides are $15 per square meter. And the top is $4 per square meter. Okay, cool. I saw somebody asked me a question on this yesterday, and they had a really nice organization component to it. It was clear, anybody reading it could follow what they were talking about, and that's the hallmark of good math, is it's can be followed by somebody besides yourself. And it's correct, obviously. What about the cost of the top? How do I calculate? 4x squared, okay? 4 is not enough because it's $4 per square meter, so I'd have to take into account how many square meters. What about the cost of the bottom? 8x squared. And what about the cost of the sides? Let's take it slow. So developing it, 15 times 4xy, all right? Y'all see where we're coming from there. Total, all right. Now that's obviously not in terms of x only. 12x squared is fine, and 60x is fine, but what can I put in for y? And what relationship do I use? Yeah, the volume is 300, and that's x squared y, so that implies y is 300 over x squared. So simplified, that's 12x squared plus 18,000 x to the negative first, yay? All right, that's A. I imagine we're going to now minimize costs. We're going to minimize costs, so what should I do? Take the derivative to find where cost is decreasing then increasing. So that is 24x minus 18,000x to the negative 2. The critical numbers are when that's 0 or undefined. That's not super easy algebra, but you guys are pretty practiced with this. But how do I solve this? I heard something about denominator. I agree with that. Then what? Find a common denominator. Love it. X cubed minus 18,000 over x squared. All right, so C prime is undefined if x equals 0, but obviously that cannot be. Volume could be 300 if x is 0. So that's not possible. It's a domain issue. C prime is 0 if x is the cube root of 18,000 over 24. Does that come out clean or is it ugly? It's ugly. Do you have the decimal in front of you? Let's just call it that, okay? I'll just call it x for the best x. You with me? Okay, so now we have the x. Question says find the dimensions. So we're almost done. I have the x, which is 2 of the dimensions, but I need y. How do I find the y? 300 over that squared. Those are both in meters, I believe. And I believe that satisfies part B. C, check the answer of the graphic calculator. You don't need to do that, trust me, we're killed it. All right, 23, question on 23.
Yeah.
All right, 23. Yeah, this is kind of wacky. The rectangle's area remains constant at 200 square meters, both width and length change with respect to time. Could both of those grow or shrink together, or do they have to both grow and shrink opposite? If their area remains constant, could they both be growing? Surely not. All right, so area is always 200 for this rectangle, so that's the starting point. Area of a rectangle is length times width, and they're telling me it's always 200. Find an equation that rates W, dl dt, and dw dt, but does not contain L. Okay. What should I do? Seems like we should take a derivative with respect to time, yay? Leave this out of it. The area is 200, so take the derivative on this piece. 0 is by product rule, yeah? That's what I was talking about in the notes. Don't be a knucklehead and forget to use the product rule. That would be a disaster. All right, so there's an equation of 4. They said to dump and not use L. What can I put in for L? Yeah, 200 over W, dw dt plus W dl dt. All right, I think that satisfies part A. Cool. Part B, if the length L is increasing at a constant rate of 15 units per second, at what rate is the width W changing where W equals 2? All right, so what are they giving me? This is verbal calculus. The length L is increasing at a constant rate of 15 units per second. This dl dt is positive or negative? Positive. Be intentional about the sign when you interpret calculus. 15 units per second. And I think they said W is 10. So we can put that there and there. And that leaves us with how the width is changing. Better be negative, and I think you'll see it is. Does that get you started? Alrighty. 25 is No, maybe I don't know. All right. Find the value of x for which the lines tangent to y equals log and y equals 2x squared will be parallel to each other. You don't really need a graph to do this problem, but just so we understand what's going on. There is some place where the derivatives are parallel to each other, or the tangent slopes are parallel to each other. So the idea is a verbal connection. What does it mean if the tangents are parallel? Tangents parallel implies slopes are the same, which implies derivatives are the same. All right, so we take the derivatives of each side. 1 over x equals 4x, and we solve. 1 equals 4x squared. 1/4 equals x squared. X is technically plus or minus 1/2, but by domain, it must be the place that x is a half. That answers the question. Yes. All right. You follow? Okay, and then the replacement problems. These were just recall, yeah? Okay, so this is our tangent and our sine. Excuse me. This one I don't have my key made. Do you want to just do them now? What do you say? What's the first step? Secant of both sides. Because we don't know the derivative of arcsecant, we're going to take the secant of both sides. Theoretically, we do know the derivative of secant. What's the derivative of secant? Yeah, so now I'm going to take the derivative of both sides, and that is absolutely the derivative of both sides. When you think about saying we multiply by d over dx, that is garbage. You know nothing about calculus, but you would never say that. So that's secant of y, tangent of y, but by chain rule, then times the derivative of the inside, which is dy dx, yeah? You take the derivative of the outside, but then times the derivative of the inside. Implicit differentiation, you should always pick up a dy dx. Derivative of the right is still 2e to the x. Solving for dy dx is 2e to the x over secant y tangent y, which is lovely, but I cannot leave my derivative in terms of y, so I need to replace. That's where this guy comes along. Draw a triangle based on the secant y equals 2e to the x. Make it a ratio. Y is the angle, and what is secant the ratio of what sides? Hypotenuse and adjacent. Cosine is adjacent to hypotenuse. Secant is hypotenuse and adjacent. So the hypotenuse is 2e to the x. The adjacent is 1. And the opposite side then is 2e to the x squared. That's a little messy. Minus 1. With that then, we can substitute in place of those. Now secant y, we actually knew what secant y equals. Secant y is 2e to the x. But tangent y, by opposite to adjacent, is 2e to the x quantity squared, or 4e to the 2x minus 1. Those drop out, so it is 1 over 2e to the x squared minus 1. Right? Y equals e to the x, like this. This is left 3, up 5. So I'm getting something like this. And it says calculator, and it doesn't say x or y, so I guess you could use either. If I use x, how many integrals would I need? 1. If I use y, how many integrals would I need? 1. So it's a bit of a wash. It's either one. Did you use, I imagine you probably used x, but I could be wrong. Did you? Did you use x or y? Yes.
Or X.
I thought you were messing with me. All right. So let's say we use x. Now, if I were doing this by hand, which would make the intersection points a mess, but I would definitely use the e to the x version, not the log of y version, because I don't want to integrate log. Come on, baby. Grow. Okay, so do I need to do this, or do you want to just check your answer? Do you feel like you did it right? You just want to verify your answer's right? Let's throw some answers out there and see if you agree with your colleagues. I don't have it done. Anybody? Does anybody have this set up with integrating by x? Negative.
2.9929.
That sounds about right. 2.
1.885.
I like it. And you're using x, I assume those are x values. And so you're using upper minus lower. What's the upper? Lovely. And what did you get for an answer? Seems reasonable. Okay. Let's go with that. If you have a question or you'd like to do it with y, that's a good exercise. Here we go. Y equals x squared and y equal 2 to the x. All right. Let's start with intersection points. Either way will mean intersection points. So, 0 and 2, yay? X equals 0 and 2, which means y equals 0 and 4. All right. So if you use x, copy this real quick. Oops, or not. All right. All right. All right. Well then, anywho, never mind. I guess I won't make a copy of this. But at any rate, if I use x, don't my rectangles go this way? So I'm going to go 0 to 2 on the bounds, left to right, dx for the base of each of those really good slices. And the height is a vertical distance, upper minus lower. So the upper is 2x. You should not use a calculator here. X squared minus x cubed over 3 from 0 to 2. That's 4 minus 8 thirds. Did you get 4 thirds?
Yep.
Okay, now we should certainly get that same answer when we use y, but the work along the way will be different here. If I use y, then the slices go this way. The area goes from 0 to 4, low to high. If you're using y, use low to high. And the bases of the rectangles go right minus left to be positive. So now that right is the curve, but it has to be in y terms. So use x equals root y first minus the line in y terms, which is y over 2. Antiderivative of y to the half is 2/3 y to the 3 halves. Antiderivative of y over 2 is y squared over 4. 0 to 4. So I get 2/3 of 4 to the 3 halves minus 16 over 4 minus 0. 4 to the 3 halves is, if I half it first, that's 2, cubed it, that's 8, times 2 is 16 thirds. minus 4 is 12/3, and therefore, there's 4/3 either way. Cool? I think that was all the replacements. All right. Is there anything else on 60?
Is there a review maybe tomorrow?
What?
The review will be tomorrow then?
No, I'll take it the day of the final. But I'm going to go over it tomorrow, so you'd be wise to have it done by, sorry, 24th. Yeah. That's for, if you want to, basically, this would be, you're saying, what is this e to what power? Obviously, it would be something different. So, I would start by getting rid. There's a couple ways to do it, but if I want e, I took the natural log of both sides. And the reason is, I can't remember, quite frankly, why I did that. Yeah, I don't like the way I'm explaining this. Okay. Do you agree with the question? I'm supposed to make 2 to the x into e to something, yeah? I really want to know what is that. So ignore the y for a second here, just blow that off. How do I get that? Anytime I have something I want to find in an exponent, it helps to take logs, right? So the question in my mind is, should I take log base 2 or log natural log? Now, if I want to find this, then I want to dump this. So I'm going to take the natural log of both sides. So question mark is log of 2 to the x. So what does that mean? 2 to the x equals 2 to the log 2 to the x. No, e to the... I don't like this at all. Yes. Is that what you want? Maybe the question is confusing myself. I guess that's cool. So there you go. Sure. I don't like it, but I guess that's all I see. So I don't know if I'm thinking about it wrong. Is that what their answer is? No. Okay. Oh, I think that's right. Okay. All right. That's So that, but I'll check the answer in a second, but I think so.